Hello everyone, and welcome back to the Fluctus channel. Ever since the first jumbo jet, the Boeing 747, made a revolution in the airline industry back in the 70s, the need for jumbo jet engines has become inevitable. Only a few companies in the world are known to manufacture the engines that take these 200-ton monsters to the skies. For the leading aircraft engine manufacturer, like Rolls-Royce, developing a jet engine is a lengthy process. It is known for its finest and most powerful engines, powering the largest known airlines, like Airbus Super Jumbo and Boeing Dreamliner, among others. The engine is one of the most expensive parts of the plane. About 11,000 people are employed to build Rolls-Royce engines across the manufacturing facilities in the UK. The star product of the company is the family of Trent engines, with Trent 700 being its biggest seller and Trent XWB, the world's most efficient large civil engine. The latest generations of Trent are characterized by lower emissions, saving airlines millions of pounds in fuel consumption. The $140 million Trent engine weighs at least 5 tons and is built from modules of 8 separate sections. Each module is made of hundreds of components, which are stored in the massive parts warehouse. The engine fan case, housing the wiring, pipes, and fan blades, is where the manufacturing starts. Unlike typical jet fans, this one is designed to be hollowed for better airflow. At the heart of every engine is a ring of 96 turbine blades, which will channel air smoothly into the engine. Rolls-Royce employs software designers to include the company's patented tiny air holes to prevent the blade from melting in the building process. The front-spinning large fan attachment is the next step. The enormous fan is what distinguishes this jumbo jet engine from older turbojets. The blades are made from high-quality metal and are designed with world-beating performance and noise level. One fan has 20 blades, each worth as much as an average family car. Weights are bolted on the inside to balance the fan and ensure it works to specifications. Any imbalance would cause major problems for the engine. The next step is to join the combustor section to the intercase. This is where the engine with the shaft connects out to the gearbox. Once the final and biggest modules are in place, the engine is fitted with aerodynamic ducts and is ready for testing. Engine testing is perhaps the most impressive part of manufacturing, which is usually conducted in a test bed. It's a big spacious room with a huge structure keeping the engine in place. Testers explore how effectively the engine handles starting up, emergency shutdowns, and even run-ins with strange objects while it is on the testbed. Additionally, thrust is monitored to check for any imbalances that can affect how the engine operates. The fan blades of the engine also go through vibration testing, which includes a nozzle blowing compressed air that invokes flutter on the fan blade to examine and evaluate its robustness. Rolls-Royce's biggest competitor, General Electric or GE Aviation, is dealing primarily in aircraft engines and avionics. Today, thousands of employees work across 80 facilities spread throughout the globe, equipped with high-pressure compressors, lean-burning combustors, and lightweight, durable materials. The engines are well-designed and developed, with over $1 billion spent yearly on the research and development. GE Aviation also became the first to introduce composite fan blades in commercial aviation with their GE90 engine, which can be seen powering the Boeing 777 fleet. Measuring more than 4 feet long and weighing about 50 pounds each, the GE90 fan blade is made from carbon fiber and a toughened epoxy matrix. The unique curved design makes it larger, lighter, and more aerodynamic than conventional titanium blades, making the GE90 more efficient and economical. The comprehensive test program includes long-lasting icing tests, ground runs, fan blade tests, and many others to ensure its airworthiness. Once approved and certified, the engines can roll out for full production and delivery to their respective aircraft manufacturer. For installation, their engines are placed into pods to prevent any direct external damage to the engine and provide wing bending relief. The podded engine is then attached to a pylon, which offers a safe distance between the engine and the wing, in case the engine catches fire. Using robust super alloy bolts, the pylon is attached to the aircraft, mounted slightly forward of the wing to prevent the wing from fluttering. While a great number of efforts are put into the commercial airline sector, a few aircraft manufacturers, such as Airbus, also thrive towards offering robust flying machines to the military. For instance, the Airbus A400M Atlas, a 4-engine turboprop military transport aircraft designed as a tactical airlifter with strategic capabilities. Being deployed as a transport aircraft, its major component is fuselage, which entails a meticulous construction process. This process's first and most crucial activity is positioning its fuselage sections. The sections must be perfectly balanced to ensure the safety and performance of the aircraft. 3D printed devices are also used to position brackets of the fuselage in a timely and efficient manner. Once the structural assembly is completed, the aircraft is then headed toward the paint shop. The process starts with applying a surface protection on the inside of the fuselage, after which the interiors are completely sealed and the exteriors are painted. Three coats of paint are applied to the aircraft using a high-volume, low-pressure spray system to ensure an equal coating. An environmentally friendly primer is used first to prepare the surfaces for the succeeding paint applications. The next step is for the painters to apply an undercoat of background color. Since the A400M is a military aircraft, it is expected to withstand extreme missions during its service. Consequently, it goes through a series of tests and qualifications, such as ground-based structural tests, flight test campaigns that include flying the aircraft for more than 10,000 hours. Besides private aerospace companies, the U.S. Air Force has its own Air Force Research Laboratory developing advanced manufacturing robots, which will help enhance human safety, improve quality of manufacturing, as well as reduce costs. For instance, the 22,000-pound A5 robotics system is the first versatile robot created for use on the aerospace factory floor that can function in a confined space using real-time sensor feedback. The A5 robot is expected to significantly reduce depot maintenance periods for aircraft coating removal by taking advantage of advances in man-machine interface technology, saving time and money throughout a platform. The A5 is unique in that it can move about an aircraft while using cutting-edge sensors to perform real-time path planning and analysis. An onboard computer receives sensor data, evaluates it, and sends an operator's approval of an optimized travel plan for maintenance operations. A5 can adapt to many platforms due to this processing power, without the requirement for system reprogramming, which extends maintenance activities' time and expense. For the Air, Space, and Cyberspace Forces, the Air Force Research Laboratory takes the lead in the research, development, and integration of low-cost war-fighting technologies. The cutting-edge technologies used in modern jet propulsion have made a tremendous impact on the development of advanced powerhouses in aircraft today. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.